Oh no, we're okay. Got my Apple Pencil. Can you see me? Can you see each other? Can you see each other?
Only if we want to.
Oh, I see. Yep. I don't remember how that works since I'm always the host. No, I go to other meetings, but not usually too much. I don't pay attention. So okay, so let's continue with this. All right. So there's a little bit of polynomial. You remember we were talking about polynomial, putting in like the x1 squared, maybe x2 squared, maybe these interaction terms into the model. And we looked at one last time similar to this example here. And I'm just going to write these sometimes like this, EY equals this, but it's because you know what we're doing now. This is the full MLR model. I have a plus epsilon yi equals this with all the I subscripts plus epsilon I, IID normal 0 sigma squared. And but I'll just for shorthand just focus on the regression function here. It makes it just easier to write for one thing. Okay, so actually when you see this EY, you should think the vector y, the vector x. That would make this a little bit not clear what this means, but really doesn't, so it isn't real linear algebra. It just means multiplying term-wise. So it really does mean EYI equals 10 plus 2x1i. I'll maybe start writing it like that when I need to, but does that make sense? It's got to mean x1i times x2i, right? From that row, there's an interaction term. Should we put it in? I'm getting worried now. So actually the i's first, right? We don't need to rush. Okay, yep. All right. All right. So then EYI, we're just gonna is what? Okay, so what I do is I just put in a 1 for xi2 here, and so this would be like fixing this at 1. Everywhere I put in a 1 for xi2, and I get a 15, I think, for the constant term now, plus 1.5 xi1. And if it's 3, I get 25 plus 0.5 xi1. And I drew these over here. So down here is x1, and up here is y. Okay. Makes sense. You get these two lines. So if I hold x2 fixed at 1 for say every I, then this explains how the first predictor is related to y. And if I hold it to 3, then this explains it. And the point is here that this interaction term changes the slope here. So when we didn't have the interaction term, all that happened was they were shifted. But when you have the interaction term, it changes the slope. In this case, right, when xi2 is increasing, it makes the slope decrease because of the minus sign here. So eventually the slope would go negative if x2 was, say, or flat even, right? If x2 was 4, it would be a flat line. So you can understand this way, okay? You can reduce it to an SLR model for each one of these cases at a time. But still, overall, it's still this model. It's still this model, yi equals 10 plus 2, xi1 plus 5, xi2 minus 0.5, xi1, xi2 plus epsilon I, where that's normal, probably normal error. So it's still, the main takeaway is it's still an MLR model. Nothing has changed. Still same as before, same as chapter 6. Okay.
So, Professor,
Yep.
wouldn't it be A of yi? Wouldn't we add the xi term and that would be like 2.5 and then shouldn't be 2.5 xi1 and then it should be 3.5 xi1, or am I?
Isn't it minus here though? It's like,
Let's
it's a
see.
minus sign. Yeah, sorry if it was clear.
Sorry.
Is that better?
Yeah, thank you.
Yeah. Yeah, I think we did, so if I remember right, we did a plus one at the end last time, and it was that. So
Got it.
this is not really a recap, it's new, it's just a continuation, but it's very similar, right? So this is actually brings up something that I didn't have in the notes here, but if this is negative, the interaction terms that are negative, so the minus sign means it's called interference. Interaction. Long words for me to write with this. This is actually harder to write on this thing with my arm situation, which is much better, but still. Interference, interaction. So yeah, if it's a negative sign, if it's positive, it's called reinforcement. So let's just mess up the whole notes. It's cool, right? It's fun to do. Positive means reinforcement. So when they get bigger, it just even bigger, even the slope gets even bigger. Might go from negative to positive or positive to more positive interaction. This case, we have a negative interaction, which is called interference. Okay, yeah, so it's still, the thing is, like, you really almost don't need to know anything new. All these things we're talking about, we talked about before, how the interpretation is holding all other coefficients, all other predictors fixed. You know, if I increase x1 by 1, then, you know, I could see the slope here. So it's all still the same. I'm just plugging in particular values here just to look at it and see what it looks like. So I don't really have anything more interesting to say. I don't even have, it's not a real application, so it's just some numbers. But you can see it just reduces this way, right? So, you know, you can do now, if you didn't know these are probably estimates from somewhere. If these were just betas, you could still do all the MLR chapter 6 inferences on the betas, just like before. Find confidence intervals for the betas, find confidence intervals for E of Y, find predict new values of E of Y. Everything's the same. Only thing is, you just added this new variable, which happens to be a function of the other two variables. Nothing else. Nothing else. Therefore, it's a pretty quick chapter. It's important though. I mean, this stuff it's used a lot, so we want to mention it and take a minute and see it. But that's what it is. Yeah, and I think the homework, the chapter 8 problems in homework 5 are, I'll talk about the test too in the exams. I just noticed that later, but this stuff, the imminent assignment will get you all you need really from this, to get you the depth more than any of this stuff in the lecture here. So, any questions? So, one other note about this, and this is kind of building on the last lecture too, is that you might wonder, okay, do I include the quadratic terms? Do I include interactions? If I have maybe 4 primitive predictors, like 4 things, and then I'm combining them as interactions and higher orders, it's getting pretty complicated. Which ones do I include? Well, you can just use your partial F-test stuff for that, just like before. So yeah, so did I filled in it. So I left this blank to make it fun. So if in this above example, how would I test whether or not to include this? I just use the partial F-test. So I might do something like SSR x1, x2, given x1, comma, x2. I'm just thinking of it as 3 predictors. Here, the degree of freedom is 1. This is a single new predictor here. I'm not gonna center this in this example. We talked about when we had x1 squared versus x1. Those, especially if I know x1 is positive, then it will tend to be pretty highly correlated. So we were centering them. I'll make it clear if I'm centering them or not, but you don't always need to center. And for the interaction terms or the qualitative terms, you're probably not going to, well, I don't know. You're not, it's going to depend. So I'll just be clear about it. And then over SSE, remember, this is not the R squared thing. This is the partial F test. So this is the SSE of the full model. So it's x1, x2, x1, x2, and then divided by the degree of freedom, which is whatever n is, minus what?
Would it be n-4?
Yeah, yep. We have 3 predictors in the full model, and P is for parameter, right? Not for predictor. So add that extra 1. So n-4 for the beta 0. Yep, right. So I could set that equal to that, and then just like before, we would find a p-value. Does anybody want to go for the p-value in terms of R code? For practice.
1 minus.
1 minus, very good. 1 minus
Yeah.
PF, personal foul.
And F star.
F star.
The degree of freedom for
Right, yep. n-4.
yeah.
Oh, 1, the numerator degree of
Yeah,
freedom.
1, yeah. So numerator, so 1 and 1 is 4.
Yep, that'll do it. So that'll give me the p-value. If it's less than 0.05, I could, I would say, I would keep it, right? If it's greater than 0.05, I might, or whatever threshold you like, I might say, okay, I don't need this after all, and take it out. Okay, yep. Okay. So to check for x1, x2 being significant, I'm not going to write everything. You have this. Oh, am I recording? Yeah, okay. I didn't want to do that again. Do it later or something, but okay. I mean, probably only a couple people will watch this. It's okay though. It's there, we're doing it. All right, so let's talk about qualitative predictors now. I know it's going a little fast, it's okay. So qualitative predictors, I want to start this with an example. This is the same example in the textbook. Nothing wrong with that. Kutner or Kuttner, I don't know. Y equals months until adoption. This is this is studying financial companies and how long it takes them to adopt certain innovations, a certain type of innovation or something. And it's measured in months. X1 is measured in dollars, assets. I'm not sure the units. And X2 is an indicator, a qualitative predictor, also an indicator. Indicator is a qualitative predictor that's usually just 1 or 0. That's 1 if the company works with stocks, and 0 if it's mutual funds. Okay, so it's a 3 predictor model. There's no interaction. We're shifting to this idea of having of what it means to have qualitative predictors. This is in Canvas. Here, let's look at it. Let's take a second to just switch over to this. Let's stop share. Seems almost not worth it, but keep forgetting that. Canvas. All right, I don't know what kind of crazy, yeah, I was in my music thing here. So I got AC/DC and all this blues and stuff, but I have other stuff below. So, okay, so here's the, can you read this text? Yeah, okay, so here's the data. I just wanted you to get a look at it. So, you know, the first one, I don't know, probably millions, maybe billions. 17 months, this the size of the company, and this must be a mutual fund company, right? Something like this. I don't want you to see my musical taste. Okay, so this is the example that's going to be in the example, but we're not going to look at it again. So one thing you can see, I think, what's one of the biggest sized ones is here is 295. It's 11. This one's very small, 92, 31. They tend to be bigger. So I think the slope is negative. In other words, according to this data, the bigger the company, yeah, I don't find this intuitive, but the bigger the company is, the quicker they adopt the innovation. Apparently, does that make sense in finance? Maybe it does. Does it? I know I got finance people out there with Diana and Dylan, other people, Sugumi, econ
Yeah.
people. Yeah, so I mean in engineering, I would think it's the other way around, but yeah, it might make sense. Okay, so they certainly have a bigger buffer to if it's a dangerous thing, and the smaller companies may be less willing to take risks or something like that. Okay, so this is this for this example. I'm probably not going to write this all out, so I just wanted you to see it. So it's not very big. I have the N down here, written down here somewhere, but I'm not sure what it is. Okay, so let's share again. Screen. 60 minutes today. Unless you want to stay on, we could listen to some music together after and stuff. Okay, I'll do a whole, I'll DJ for you for your study session after if you want. That's optional, but there will be extra credit for that. Okay, let's see. Yeah, no, I'm kidding. Okay, so let's go here. So this is what I have. That was just that data. I'm sort of summarizing it there. And I think I'm out of my notes. I was here a little early, so I started to just write this out. Yeah, so this is just MLR like this. And let's what we can do a similar thing sometimes when you have like interaction things in terms of other predictors, or you have qualitative predictors, you can sort of simplify this. So let's write it like this. This equals, and I've returned to getting rid of the I because I think it's clear. And R kind of works like that anyway, where you're not using for loops so much, you just put in the variables. So and it knows that you want to iterate and do things term-wise. Okay, so we could do this in a couple ways. Like I could write this like this. It's equal to 2 things. if X2 is 1 or 0. So if it's 0, I just get this back again, and the last term is gone. But if it's 1, then the intercept increases by beta 2 or decreases. Plus. So you can see I can break it into these two pieces. There's this constant change based on X1, on the size. There's this trend based on the size, but then there's a constant shift because I guess a shift upward because the stock companies are less innovative than the mutual fund companies. Again, this seems almost counterintuitive to me, but okay. It's different. Finance is different than engineering, so I get it. Okay, so anyway, this is just an example from the book. So let's just draw this out. You don't have to know anything about this to do this. So let's see. Do I have an estimate for this? Yeah, when I did this, I put this into LM, right? So we type LM. And what do we get? LM, let's say, just call it, I don't know if you remember the names of those variables. We'll just call it so that we don't have to remember that y as a function of x1 plus x2. And we get some estimates here. I do get a little B0 estimate and a B2 estimate. I don't think I wrote everything down. Yeah, I didn't write everything down, but anyway, I get a positive B0. So for this, I get some B0, B1. This is negative. This is positive, okay? And so I'll put this in greater than 0, less than 0, and then I get a B2. This one I did write, and this was approximately 8.05. Remember, this is months. Okay, so if I'm going to represent this over here, then I'm going to make it two cases. So I'll have this case where it's something like this, and another case where it's like this. And I have, first of all, if I were to try to sketch this with all three predictors, it would be three-dimensional, right? So if I take out all two predictors, if I take out the second predictor and sort of treat it, since it can only be two things, treat it as two cases, then I get a nice, it reduces to two SLR models. Okay, I'm relaxed. So we'll get to this. So let's explain this a little bit. So let's do it together. So which one, do you remember, which one do you think is the stock line and which one is the mutual fund line?
Stock will be, I don't know, lower.
The stock, so the data was a 1 if it's a stock, right? So that corresponds to this one. And then
Wait.
we saw that B2 is about 8.
Okay, then higher.
Yeah, the
Sorry.
stock is the top one, right? So this is stocks. Let's just write stocks. We could write X2 equals 1. Be a little more mathematical and less comprehensible. X2 equals 0. So the mutual fund one is less. And actually, yeah, so for a fixed size, if I took a company of the same asset level, then, and I'm not trying to teach you anything about corporate finance. I don't even know if this is true. I don't know anything about it. Okay, so if I take a company of a fixed asset level, call this X1 and Y, then we could see the mutual funds tend to take this much time to adapt the innovation. This is about 8, so maybe this is 5. And oh no, the difference is 8. So I don't know what this level is here, but it would be, say this is 5 or something, and then the stock one would be at about 13. Okay, it takes roughly, the expected difference is 8. The estimated expected difference in months to adoption is 8 for stocks versus mutual funds. So you can analyze it this way. It makes sense if you have one predictor or even multiple ones, make different SLR plots for all your different possible scenarios that you're considering. So if I had 3, I would just have, I could set whatever I want, whatever combinations, like think of a binary word or something. Okay, so well, I did this actually say we wanted to find a 95% confidence interval for B2. Again, the big lesson here is I don't want to do that though. Yeah, the big lesson is it's exactly the same. You're just working with things. So far, it's exactly the same. All I've showed you is that it can be a little easier. You can now make these pictures, which really would have been difficult before. Okay, so say we want find a 95% CI for beta 2, the difference in, which is the difference in expected months to adoption. Okay, so same thing, exactly the same thing. We would have we have B2 would be the center, and then it's plus and minus SB2, and just LM will do this for you. SB2 plus this times, what is it, QT? 0.975, right? Since I want a centered confidence interval, and it's N is 20, but let's just say N minus, what should it be?
3.
Yep. Yep. And if I do this, I get this is about 5.0 to something like 11.1, something like that. So as a lower bound, you could say I'm 95% confident. You could even say even a little higher because you're not closing it on the right. If you wanted just a lower bound, I'm 95% confident though that the expected time to adoption is at least 5 months more for a stock company than a mutual fund company. Okay, one thing you might wonder is why don't I just get rid of the indicator variable altogether and just make 2 SLR models, one for the stocks and one for the mutual funds, and then just compare the expected Ys at the same level. That would avoid having to even use MLR, right? So why not, why is that not an option? Actually, it is an option. Why is this better though? Any ideas?
Because you can compare.
Yep, something about that. More detail. Well, think in general. Okay, maybe for this little example, maybe it's not that interesting or it doesn't make much sense. I think it does, but I mean, in general, too. Yeah, I think anybody or ruin it for Yeah, I think the reason is, you want as much data as possible, and the X one, right, is it's good to get all of it together. You don't know if that's different. The size factor is different, right? Since you have different sizes across both cases, you might as well take it, at least you might as well, and it might really be important to take it across both. So that's the idea, is you want as much data and as much information as possible. So say you had more than two, you don't want to get smaller subsets and say, oh, I got this for, I had 5 cases here, so here's my SLR here, and 25 here. No, take all of it, but separate it out in this way and look at these things marginally with the full data set. That's the way to go, usually. Okay. No more about that. Okay, I want to do one more on this. And, in fact, we may just be starting nonlinear next time. I don't know this. It's a good class. It's a good, so far it's good. And it takes what it takes, right? And we got time, actually. I've planned it out. So let's do one more example here. There is an important thing to note, which is that if you have more than 2 cases, in other words, if you have a qualitative predictor with more than 2 levels, or you have more than 2 indicators, there's a special rule that's important, or your model probably could not work, maybe. So I'm going to do this just with an example. So, because I don't want to write too much, this is also in the book, and this example's in the book. So we're going to let y equal something like motor wear or something like this for a certain small engine tool. And x1, so it's similar in a way to the previous example where we have one of the things is continuous variable, and then I have qualitative. So x1 is highest speed, or let's just call it speed, motor speed. But instead of stocks and mutual funds, I'm going to claim we have 4 different models with different speed profiles. So x2 will be equal to, now you could think of it as 1, 2, 3, 4 for the 4 different models, but for now I'm just going to write M1, M2, M3, M4, which is model type. And hey, your data can have text strings, right? So think of the column as being a text string that says M1, M2, M3, M4, okay? Character string. All right, now, what could you do? So this is a character string. This is an integer or a float, double. I don't know if that's what Art calls it. I don't remember anymore. But I know, I just don't always remember. Okay, so what would you do here? You got these text strings. Your boss needs it by this afternoon. What would you do? You have to make a model and tell her what's going on as far as the model types and speeds and everything. Everything. Full thing. Diagrams, presentation by 4. Just teasing you guys. Okay. I'm just teasing you. Okay. No problem for you. You took this course. You'll have it done in an hour and you'll be walking out in the park, enjoying the day, coming back at 4. Okay, so what would you do? 2 options I can think of, right? You want to use an MLR, right? So one thing is you can think, I could just let a integer just be like 1, 2, 3, 4, right? Set that equal to 1, 2, 3, 4. Convert to an integer 1, 2, 3, 4. However, this may be tricky, right? Because what if 1, 2, 3, 4 usually means it has stuff associated with the mathematical object called the integers. So we don't know that the model types also obey those rules. In fact, they certainly don't. So tricky. You don't want to make your model too tricky with trying to interpret or encode things. That's not good. It doesn't make sense, hard to understand, and may even just be completely misleading or impossible. So not a good option. What else could you do?
You could make a separate qualitative predictor for each model type, but then again, that'd be redundant because you only have one model type per motor.
Yes, no, you're right. That's what you want to do. You want to make a separate one for each that's 0 or 1, right? And that way, I mean, you wouldn't have two of them set to 1. It's a bit redundant. Only one can be set to 1. In other words, you're technically keeping room for 16 types, but you're only going to have use 4 of them. The only thing is here, and I don't want to write all this, it's also written in the book, but the only thing here is you don't want to use 4. And the reason is, if you use 4, you're going to build out an X matrix that has rank less than, it's going to be a dependent X matrix. The columns it won't have full rank, and your X prime X won't be invertible if you use all 4. The reason is, think about it, if I have those columns and only one is set to one of those and the others are 0, then your 1 matrix, your beta 0 vector is simply the sum of those 4. In other words, let me just write it kind of simple. Say this is your 1 matrix in your 1 vector in your X matrix, right? But over here, I got this like that says if it's M1, right? And then let's say those are the only 2 that are M1. But then I have one here that's, M2, and let's say those are the only 2. And then I have maybe these are, and if I just add these up, right, I get this one. So, they're dependent. So you can't do that. But don't I know everything if I know 3 of them? I know everything, because if I get all zeros, that means it's M4, so that's the trick. Okay, so trick is include C minus 1 indicators. We'll use the word indicators for models for a qualitative variable. Let's call it a variable with C categories. Okay, so if it has C categories or types, I'll add C minus 1 indicators, and that will completely specify which type it is. Make sense? So if they're all 0, it means the Cth type. If the first one's 1 and the others are 0, that means the first type. Second one's 1, the others are 0, that means the second. They're all 0, it means the last type. And I'm not including that because I want to have this potential to have this vector there too. I mean, you could think, well, why don't you have the 4th one too? Actually, that'd be a total valid way to do it as well. You could force it to go through 0 and take out your beta 0, 1 and add the 4th indicator. That is valid. But the way the book does it and other people do it, I think, is to do it this way. So, sorry. Okay, so we're gonna do it this way. All right, so let's look at this example then. So let's let we'll let x2 equal 1, 0, x3 equal 1, 0, x4 equal 1, 0. I'll have this be if M1, else. It's a little maybe confusing because of the indices are off, but it's okay. ML 3. So if it's the fourth model type, these will just be 0. Okay, so what do we get then? EY given so yeah, I think we could do it like this. Given x2 equal sorry, I'm calling it x2 now. Let's just say x2 given, let's just write model the word out. So what is the expected value of y given, let's just write this, M1. Okay, well, I should probably write the model then would be here. So let's write, we'd have y or EY equals beta 0 plus beta 1, x1 plus beta 2, x2 plus beta 3, x3, beta 4, x4. Okay. EY given M1 then is, all these would be set, this would be set to 1, all these would be set to 0, so I get beta 0 plus beta 2 plus beta 1 x1. EY given M2 equals beta 0 plus beta 3 plus B1 x1. Yeah, a little tedious, but I want to do something with this in a second, so I'm doing this for a reason. Equals beta 0 plus beta 4. And then finally, EY M4 equals, anybody?
Beta 0 plus beta 1 x1.
Right, all those other ones are 0, so they're not in it. So it's just beta 0 plus beta 1 x1. Right, okay, yep. And now, what might I be interested in? Same sort of type of thing, usually. What's the difference in expected motor wear between model 3 and model 1, for example, or anything, or you know, what's the variance or the what's a confidence interval for the expected wear if it's model 4, or joint confidence intervals for model 4 and model 3, things like this. And all of this can be done. We have all of it. Nothing is different. That's why so fast. You did all this. That's why we worked hard to understand that. So you could set it in new settings and do this. So, okay, so I have one little thing here. I think this might be the same as in the book. I'm not sure. So let's say find a 1 minus alpha CI for beta 4 minus beta 2, which would be the difference, the diff in model, well, let's see, this is model 4, right? This is model 3, and this is model 1. So When I subtract these two, I get beta 4 minus beta 2. So in model 3 and model 1. So in model 3, put that first. Model 1. I keep wanting to write ML from. At same speed. You could specify the speed, but doesn't matter. It should be, since it's a linear model. Okay, so I need a point estimator, right, and a standard error, and I should be good. So remember, what we're gonna do is we're just gonna run LM again, just like before. So we run LM on this model, on these variables, these ones that we defined, and we set, we know already a point estimator for so the point estimator, the center, is just going to be little b4 minus little b2. So we have E, I don't know, b4 minus b2 is just equal to b4 minus b2 from LM. And okay, what about the estimated variance then? So, or the standard error, what's SB4 minus B2? Well, I mean, you can write all the variance out. I see people already understanding how to do that. So we can just go straight to the S term. If you want to really go relate it back to Math 217, you just think, well, it's the variance. And then at the end, I'm doing the estimation and putting in the MSE. So all this is just the square root of the variance, though estimated. So we could also write this like this. If I wanted the variance of these, I need the variance of the first one, but I'm just going to put the S in. So S squared. And all that means is I just replace it with the MSE. It will come out in every term here. So S squared B4 minus S squared plus, plus variance plus S squared B2. But these are not independent, right? So I do have to add the covariance term plus S B4 comma B2. And there's a 2 here as well. Still remember that, right? And this is minus. Oh God, make it so many. It's not that I don't know it. I'm just thinking on the next step. Okay. Minus 2 S. We'll just use the single. No, this just means the square root of S squared. But if I put 2 arguments in, you know what that means, okay? Now you say LM doesn't give me this, right? Correct? What do we have to do? You have to go to the matrix. You might be able to find libraries that do this, but just go to the matrix, build your matrix out. So let me just write this, what these are. So, so this is it, right? This is your standard error. And let's write what these are now before we move on. So S squared, for example, let's call it BK, is just equal to, the squared version is just equal to MSE from your LM command that you can get, and, or use ANOVA or something if you want, and X prime, X inverse. And down here, sorry to be annoying, but I think I need to put K plus 1, right? Because we call beta 0 is technically 1, 1. And so this would be 5 by 5 matrix for this model. So if I want, say, S squared to be 4, it would be 5, 5, the fifth 5, 5 index. And S, say, B, let's just put the example here to do like B4, B2. This would be MSE X prime X inverse, and here I would have 5, 3 or 3, 5. Okay, and you just can do it this way with the matrix like this. What do you think? Does it make sense? Could you do this? So then the confidence interval, so then 95% CI, it's actually the last thing I'm writing today. We got right to the start of the nonlinear stuff, so that will be, we'll begin that in 23 hours and 55 minutes or something like that. Okay. So 95% confidence interval is, what if our class is every 23 hours or something like that? Okay, you're almost done with me. 95% CI would then be just B4 minus B2. That's my center, plus and minus this S, B4 minus B2. And then I just want the QT again. Do we want QT? Yes, it has to do with the MSE, right? So QT 0.975, and it was 20, so N minus 3. So I just put 17 in. Yep. All right, I got it. So that's good enough. That was good. We got this done. It's perfect. Actually, I'm glad we met today. Getting all of this done. Any questions? All right, let me stop recording. Try to keep it as